In this next module, I'm going to tell you about the statistics that we use to describe the variability of data. So there's a number of different statistics that we can use to measure variability. So the simplest is just to look at the range. That tells you about the spread of the data. The most common one that we use is something called the standard deviation that we're going to talk a lot about. We also might talk about the variability or spread of the data in terms of percentiles or something like an interquartile range. So the range is easy because it's just the difference between the largest and smallest observations, but that's very useful information. So for example, when I asked my students about how much homework they did in hours per week, I got a range of anywhere from 0 hours per week all the way up to 40 hours per week. So my range is 40 hours per week. So it's quite a wide range. It gives you a sense that the data is fairly variable here. Moving to the standard deviation. The standard deviation is by far the most common measure of variability that you're going to see in statistics. So I'm going to spend quite some time talking about the standard deviation so you really get a good understanding of it. First of all, however, I'm going to give you a little challenge. And if you want, you can even pause the video and think a little bit through this challenge. My challenge to you is, what if somebody were to ask you to devise a statistic that would give you the average distance from the mean? We want a statistic that tells you what is the average distance of any given observation from the mean. How would you calculate that? How would you come up with a statistic that does that? If you want, pause the video and see if you can think it out. So probably your first instinct on this is to, first of all, you have to think about what's distance from the mean. How would I quantify distance from the mean? So to measure the distance from the mean, what you're going to want to do is subtract an observation's value from the mean value. That will give you a distance. So we can represent that in mathematical symbols as xi, that's any given observation in your data set, minus x bar, that's your mean. So if you take, if the mean in the data set was a mean height of, say, 69 inches, then if somebody was 71 inches, they would be 2 inches above the mean. That would be their distance from the mean. Or if the mean homework that you do per week is 11 hours per week, and if that's the mean, and you happen to be somebody who does 40 hours per week, then you would be 29 hours per week above the mean. That would be your distance. If you only did 0 hours per week, you would be negative 11 hours per week away from the mean. So that would be the distance from the mean. So that's the quantity distance, but then how do you get the average distance from the mean? Well, we know how to calculate an average, right? So to get the average distance from the mean, your first instinct would be just to calculate an average of those distances, right? So again, in mathematical symbols, what you would do is you would add up all of those distances. So each observation in your data set has a distance from the mean. You could add all of those up and then divide by n to get the average, right? That's a good first instinct. Of course, there's a problem with that. There's going to be a problem with that quantity, right? So what's the problem with that? Well, the problem with that is it's going to fail because remember that some of the distances are going to be negative and some of the distances are going to be positive. Some people do more homework, some people do less homework. In fact, if you add up all of those negatives and positives, you're going to get exactly 0. So when you try to calculate the standard deviation in this way, it actually completely fails because you end up with a value of 0, and that's because you've got negatives as well as positives. So the problem is the negatives. So the next thing you might think is, well, how am I going to get rid of the negatives? What do we do in math if we don't want to deal with negatives? So how can I get rid of negatives? Your first instinct on this might be to turn to absolute values, right? If you take the absolute value, you could do the absolute values of the distances, and that would get rid of the negatives. It's not going to add up to 0 anymore. However, it turns out that it's very messy mathematically to deal with absolute values, right? If you remember back to like Algebra 2 in high school, when you dealt with absolute values, funny things happened, like less than signs got flipped around to greater than signs and all these kinds of funny things. So, mathematically, we don't want to deal with absolute values. So what's another way to get rid of negatives? So another way to get rid of negatives is to square things. So that's actually what we're going to do. This is how we're going to calculate standard deviation. We're going to square all of the distances from the mean in order to eliminate the negatives. So rather than take the raw distances from the mean and add them up, we're going to square those distances first and add up the squared distances from the mean and get the average squared distance from the mean. This is something that we call a variance, and in terms of symbols, I represent this as an s squared. S will be the standard deviation, so s squared is what we call the variance. So s squared, the variance, is the average squared distance from the mean. and I'll just write it out one more time here formally, I just want to point out that the official formula for variance, which I've now got up, we've gotten to the official formula here for variance. Again, S squared is the symbols I use to represent a sample variance. Notice that the formula looks just slightly different because there's in the denominator, I'm not dividing by n to calculate the average, which is the way we usually calculate average. I'm dividing by n minus 1. This is a little technical point, but I just want you to understand why it's there. So it turns out that the reason we're dividing by n minus 1 here is that we've lost what's called a degree of freedom. So when we calculate variance or standard deviation, we have to calculate something else first. We have to calculate the mean first. By calculating that mean, we lose what's called a degree of freedom, and we're therefore only have n minus 1 degrees of freedom. So that's why we're dividing by n minus 1 rather than 1. For all practical purposes, it doesn't usually make a huge difference, right, whether you divide by n or n minus 1, because as long as n is pretty big, you know, whether you divide by 99 or divide by 100, it's not going to make a huge difference. But that's why technically that's in the denominator. So what's a degree of freedom? Well, a degree of freedom is let's say I've got a data set of 100 people, and I were to give you, and I were to calculate the mean for that 100 people, let's say the mean age, and I were to give you the mean, and I were to give you 99, the ages for 99 of the other people in the data set. If you had 99 of the ages and the mean age, you would be able to calculate back for me exactly that 100th person. So that means that once you've calculated the mean, you only have 99 degrees of freedom left because that last person, that 100th person, is fixed. They can't be anything else. Once you have 99 in the mean, there's nothing else that that person can be. So you've lost what we call a degree of freedom. Again, that's a technical thing, but it will come up again. So I just want to point out that that's there. Of course, we start by calculating the variance, the average squared distance from the mean, but that would, you know, if you're not going to report the variance in your paper, because that would mean you'd be reporting things in like age squared, years squared, homework squared, hours squared, and so of course we're going to want to get back to the units of the original data. So we're going to square root it. And that's what the standard deviation is. It's the square root of the variance. So we start with the variance and then we square root it to get the standard deviation, to get back to the original units. And I use as a symbol for that, I use S. So S squared is the variance, S is the sample standard deviation. So that's just to take a square root to get back to the original units. That's what your standard deviation is. Now, I just want to point out that there are consequences to the fact that we did this little squaring routine. So the standard deviation at the end of the day is not exactly the average distance from the mean. It represents sort of the average spread or average scatter, but it's not exactly the average distance. We have this little squaring trick in there, right? And so one of the consequences of that squaring trick is that things that are farther from the mean are actually going to have more influence, are going to contribute more to the standard deviation than values closer to the mean. So for example, if the mean is 5, then if you're talking about a value of 6, you're only 1 away from the mean. If you square 1, you're still at 1. But if you are 5 away from the mean and you square 5, you're amplifying that distance. So now it's a distance of 25. So we're going to, this says is that when you have values that are extreme, those are going to have a lot of influence on the standard deviation in the same way they influence the mean. Let me just give an example calculation here of how you'd actually go about calculating the standard deviation by hand. So remember we had this little hypothetical data set which had 8 people with 8 ages in it. They ranged from 17 to 38. We calculated in a previous module that the mean for this data set was 23.25. So again, we have to calculate the mean before we can calculate the standard deviation. To calculate the standard deviation, I'm going to take each of these individual ages and subtract the mean and then square it. So for example, the person who's 17, they are 6.25 years away from the mean. So we're going to take 6.25 and I'm going to square it. The person who is 19 is 4.25 units away from the mean. So I'm going to take 4.25 and I'm going to square that. I'm going to do that for each of the 8 observations. So I end up in the numerator with a sum of 8 squares. I'm going to add those up. And then I'm going to divide here by 8 minus 1 because, again, we've lost 1 degree of freedom, so we always divide by n minus 1, so we're dividing by 7. And then to take the square root of that whole thing to get back to the standard deviation, I come up, if I calculate this all out, with a value of 6.3. What does that value of 6.3 actually mean? So again, this is trying to get at the average distance from the mean. So this is saying that roughly the average scatter around the mean is 6.3 years. Now if you notice, if you look at each individual participant here, like there's a person who's 17. Well, 17 is almost 6.3 away from the mean, but not quite. 19, 21, 22, 23, 23, 23, they're all much less than 6.3 away from the mean. So it's not looking like the average distance from the mean is really anywhere around 6. But we have one person who's really far from the mean. They're 38 when everybody else is in their early 20s or teens. That person is because they're far from the mean, they're having a lot of influence. That person is driving the fact that this 6.3 value is so high. So again, you know, if you're far from the mean, you can have a lot of influence on the variance or the standard deviation. And so that's why that it comes out to be 6.3 there.